Okay, we're live.
Great. So I'm here today with Kurt Cagle, and he is an amazing writer, technical architect, and consultant speaking in AI, enterprise metadata, machine learning, and graph technologies. So he's been an author of 22 books, which is no small feat, and he's written more than 1,000 articles for publications such as Forbes and Data Science Central, managing editor of Cognitive World, in addition to being co-founder of SDG. Kurt, thank you so much for being here.
Thank you.
I would love to pick your brain about what your definition of information architecture is.
Oh God.
So,
That's an incredible question. My own personal definition is information architecture is the way that we deal with how we structure language. Just about, we talk about data. We talk about data all the time. But one of the things that I think is increasingly becoming obvious is that what we think of as data, numbers and dates and things like that, actually constitutes a relatively small portion of the overall information space that we happen to be in, day in and day out. Anything that we're dealing with, any kind of interaction that we have, ultimately comes out as some form of information. So when you look at information architecture, it's basically a way of being able to say, can I provide the most relevant information in the most efficient manner possible to the largest potential audience, while simultaneously making sure that information that is either not relevant, not accurate, or not accessible, essentially stays in the background. And so, that challenge is really, I think, one of the biggest challenges that you run into right now in the computer space, because when we start dealing with any type of interaction, whether it's artificial intelligence, whether it's, simple data management, whether it's trying to coordinate content management through literally millions of different streams and things like that. All of that ultimately has to be engineered in some way to be able to make it useful. So that's kind of my working definition of an information architecture.
I love it. I love it. And I understand that you're writing a book about data modeling for lay people. So can you tell me a little bit about your book and how data modeling relates to AI?
Yeah, the book is something that consists right now of lots of articles and chapters that are still kind of being edited together. It's kind of looking back and saying, does this make enough sense to be germane? So I will get it out eventually. Yeah, that's what all authors say. Yeah, it'll be out. It will be out. It might be 2028 by the time it actually gets out into to people's hands. But what I'm trying to do right now with ontologists for the layperson is essentially provide a look at information management. Look at information architecture. How do we proceed to be able to satisfy those terms? Ontology, I actually had this question asked this morning. Someone pinged me on LinkedIn and said, well, how do you define an ontology? And I said, well, that's a not easy question to answer, because it really kind of comes down to, what is your problem domain? What is the information that you're trying to be able to work with? And once you have that, an ontology can then be thought of as both the collection of data models and constraints, as well as that specifically relates to, and I'm going to use the term very loosely, your business. And the nature of that can vary depending upon what exactly it is you're trying to model. An ontology is a model. An ontology is basically a way of being able to say, this is how I think about the world. Anything can be described as an ontology, but when you start talking about that ontology and with respect to what specifically is in there, um, it really kind of comes down to a lot of different pieces that people tend to know about individually, but that collectively, people are only just now beginning to come to some kind of awareness of the fact that they're interrelated. And I think in many ways, the purpose of ontology is to basically describe the relationships that exist between the things that you know.
Yes, yes. And so I have a question around that because lately within the general technology industry, those implementing AI models, either at scale and in production or trying to get there, there's been a lot of discussion about ontologies. So I think it's relevant to the data modeling space. Can you have ontologies, and can ontologies help with LLMs or RAG approaches without knowledge graphs? I hear and have seen that question quite a bit.
Well, let me actually kind of dissect that a little bit.
Sure.
Okay. The term knowledge graph, a knowledge graph is an ontology. A
Hmm.
knowledge graph is, there are many different kinds of ontology, but knowledge graph is specifically one that's focused primarily on I'm wanting to describe conceptual interrelationships, usually within some kind of a domain. Now there are some ontologies which have nothing to do with that. You can talk to anything that's schematic, for example. I can talk about RDF, I can talk about OWL. Those are ontologies that are specifically focused on, in the case of RDF, very low level thinking about relationships. Ontologies, or excuse me, OWL is something that is much more focused primarily on inferencing and inferential relationships. But those aren't really knowledge graphs in the same way. So we think about a database. A database is the thing that we have in our organizations that essentially describe a certain set of interreactions, set of events. And when I talk about an event here, I usually talk about really anything that has some kind of a history. And those events in turn are usually then tend to be classified in certain ways. So when I talk about an ontology, a knowledge graph in that sense, what I'm usually talking about is I have something that acts as a schematic definition, or a set of schematic definitions, which are the constraints of how things interact to one another. I have an ontology, or excuse me, a taxonomy that is essentially how I classify information within that particular domain of the ontology. So it's much more focused on the what than it is on the how. And then finally, I usually have some kind of an operational ontology, which tends to be well, four things actually. The operational ontology is basically what sits on the behind the scenes that basically allows you to make things work effectively. So, I've seen it referred to as an upper ontology or things like that. I tend to call it an operational ontology because I think the notion of upper versus lower ontology really doesn't make much sense. And then finally, you basically, if you look at everything as being events, then that data is essentially those events. It's the things that change. It's the history that you're basically tracking. And that history then is basically the objects that you're working with. It's the people, it's the places, the organizations, the locations, the products, all along those lines that essentially have some kind of existence. They come into existence, they basically do their thing, they go out of existence. They become relevant, they cease to become relevant. That to me is basically the definition of a knowledge graph. Now, getting back to the initial question that you had, after this long perambulation here, um, when you start talking about these kind of knowledge graphs, um, they can be represented in any number of different ways. You can do it out of a relational database. You can do it out of a graph database, which is usually how I tend to work, and I think how a lot of organizations work. You can, in theory, even use an LLM to be able to use it as a knowledge graph. There are some problems with this, and I think the discussion I caught from the last session illustrates a lot of those particular problems. And I think Michael brought up a huge list of those problems, actually. And I'm glad I was able to catch that. The biggest that you run into comes down to the fact that when you are dealing with a knowledge graph, you are generally saying, I have a known concept, and that concept has an identifier. And that identifier is basically what allows me to say, when I talk about that concept, this is what I specifically mean. Now, when you talk to an LLM has no concept of concept. It has no real notion of this is something that is a fixed reference point that I can basically build around. Instead, it's essentially a cluster of information. It's a cluster of data points. And those cluster data points have been classified usually in these massive vector stores that have 28, 30,000 parameters or more. In some cases, many, many more, very, very large database. When you start talking about, hey, this is an nth dimensional structure, and most people have trouble thinking beyond 3 dimensions, you're in trouble. So this particular clustering mechanism that we've developed that essentially allows us to work with this information is very useful in dealing with one kind of relationship. And that is to say, is something relatively similar to or relatively relevant to another concept. If I can find one concept, then I can basically sweep through this space, create a sphere or some kind of a cosine dot product or something to that effect.
Cosine.
That will allow you to say, okay, these are similar because they are in roughly the same direction, or they are similar because there is a neighborhood of other points that are all basically transformed via some kind of a transform mechanism. Is usually and I always get this wrong. TDFIF, or it should be TDFID.
Yeah.
Okay.
Yeah.
That that or BM25 or other encoding mechanisms that say, okay, this is where this thing is, in this massive latent space. And so when you retrieve things, what you're retrieving is essentially going to be a very amorphous cluster of things that may or may not actually be relevant to what you're doing. And so, the challenge that you have then with those kind of systems is that you have to basically say, okay, well, if I can essentially inject into this something that says, I have an identifier over here, and that identifier basically is going to identify this cluster, then you have roughly what mathematicians would call an isomorphism. They're not the same thing, but they are roughly similar in that what they will retrieve is something that we can talk about conceptually as being more or less the same thing. And we get into that all the time, even in the semantic space, where we don't. There really isn't a notion. There is kind of a notion in OWL where you talk about OWL same as, and one of the things that you learn as an ontologist is OWL same as is actually a pretty nasty relationship, because same as doesn't really mean what you think it means. Especially once you start thinking about pointers. If I have a concept and I have 2 different pointers, 2 different identifiers that point to that same concept, And I say same as, that doesn't mean the pointers are the same. They're usually not. It just means that the concept, which is this much more amorphous intellectual thing, happens to be um, roughly analogous to one another. And that's one of the reasons that that particular usage in general has kind of fallen out of favor with ontologists, because it is a very ambiguous terminology for something that in the real world it's very difficult to be able to say, these two things are equivalent. But if you have identifiers that you can basically then say, look, I have a space of identifiers that are all clustered, and they happen to be corresponding to that, then yes, you can sort of kind of use an LLM as a graph, or as a graph description that effectively can then serve as a knowledge graph. Again, a lot of issues with it, but it we're kind of beginning to hone in on this idea. So sorry, Des.
No, it's interesting because something that I've also run into with people in the space trying to model data using ontologies tend to think that they have to use one ontology and use every single concept or every single property, class, entity represented within that ontology. So you could take something like schema.org, or you could take OWL. But can you help everyone, just sort of get their bearings around ontological modeling and data modeling, and what that actually means to create an ontology to represent these concepts?
Um, I I tend to use RDF, fairly heavily, and it's not the only way of being able to describe information, but it's useful in that it's kind of like machine language or assembly language, that it's a very low level language that allows you to be able to articulate relationships. And one of the things that you discover when you're dealing with those relationships is that the distinction between a relationship and a thing is actually much less precise than we would like to think. My favorite example is one that actually came out of the RDF Star Working Group. Someone came up with this notion of saying, well, we have a case where we're talking about Liz married Richard. And if you happen to be of a certain generation, long beard, you probably have at least an inkling that that's kind of a call out to Elizabeth Taylor and Richard Burton back in the 1960s. So coming up on almost 60 years ago now. It's becoming ancient history, but for some of us, we actually kind of vaguely remember it. And what we remember about it most is the fact that that not only did Elizabeth Taylor marry a lot of people over the course of her lifetime, but she married the same person twice. And this is a real problem when you talk about, well, what do you exactly mean by married? Because when you get into this notion of married, you're basically talking about, here is a relationship that you think is clear until you run into this question of, oh, well, was this the first marriage? Was this the second marriage? Was, if I have someone who basically marries through 3 or 4 times, how do you basically differentiate between those? Are those the same thing, or are they different? And then you get into questions about saying, well, actually what you're talking about is there's relationships that says, I have 2 people, and those 2 people happen to have a relationship thing called a marriage. And that marriage in turn is essentially connected to these 2 people in some way. There's a contract that essentially goes in. You go to the minister of the peace or justice of the peace and say, okay, I sign my name over here, you sign your name over here, and voila, we're married. You would think that was simple. It's not. It gets to be very complex. Genealogy is such a fun topic for ontologists. Um, but when you get into that, what you then kind of come back to is this awareness that, okay, I have a thing called a marriage, and that marriage is a specific instance, and I can actually talk about two different marriages between the same people. Um, but there's still that relationship. We build those relationships mentally and being able to want to say, this is how I do it. Now, you look at a language like, or look at a construct like Neo4j. Neo4j is a very good database. I worked with it myself, a number of times. But you can make this assertion under a create statement about Liz marrying Richard, and you can make it twice, and they're actually different assertions. Because inside of that, there is actually a little invisible node, an invisible concept that says, hey, I'm a singleton property, or I'm a reification, and they actually turn out to be more or less the same thing. And those nodes essentially occur only once, or only a relationship that, have a type, have some kind of characteristics. You can basically do some kind of binding between them that then differentiates between those. And because it's hidden, because you don't see it, it's something that you just kind of naturally do. But if you go back to RDF, you can kind of scratch your head and go, I'm not sure how this relates to one another. How do I deal with this thing that I have a generalized property? And then I have to deal with a specific instance. All of a sudden, everything I thought about, I'm suddenly not sure of. Well, that kind of thinking is basically what an ontologist needs to do. They need to basically say, well, okay, what do I mean by this? And how do I define this to be able to say this is something that's unique versus not unique? How do I refer to a marriage rather than a property of being married? We build ontologies to be able to solve this problem. But we also build ontologies primarily from the standpoint of how do we deal with ambiguity. I'm a big fan of basically rolling your own ontology. You can use others to basically help you do it, but your domain of interest and my domain of interest, even if we're in the same space, probably is a little bit different. So I usually go and say, build your own ontology, build structures that make sense to you, but keep in mind that if there's something that allows you and me to communicate, that needs to basically be some kind of a target, so that there's a transformation that we can make that is predictable, that will allow me to say, when I talk about a marriage, hey, we can talk about schema.org, or we can talk about genealogy.com, or whatever.
Mm-hmm.
Each of these have their own particular standards, and we can communicate that through a transformation of information in that ontology to be able to get to what we're looking for. Now, a lot of people go in with this assumption of saying, okay, I can use one size fits all ontology to be able to build what I want to do. That works until you say, but wait a second, I have something that doesn't fit into this ontology. How do I deal with that? Well, I'm going to write an extension. All of a sudden, your ontology is no longer completely compatible. Your ontology is going to be is going to be just subtly different, but there's certain pieces of information that you can no longer interchange. So when you're dealing with this kind of information, you have to basically say, how much information am I willing to lose? What kind of fidelity am I wanting to keep? And what is the purpose of what I'm building?
And that's a great point, Kurt. I'm curious how, if we can just take a step back and look at how the design or modeling would be different for a property graph than a knowledge graph, the distinction between the two.
The distinction between the two actually comes down to what I was talking about earlier.
Yeah.
If there's a couple different ways that you can model that. One of them is to say, if I have an assertion, something like Liz married Richard, then there is actually there what you're actually doing is saying Liz marriage one Richard, and that assertion, that triple, is actually valid. I can do that just fine, except for the fact that that marriage one that we're talking about is effectively hidden because we're not because we're talking about something that's unique. Now we can name it. There's nothing wrong with naming it, but that in something like Neo4j, that kind of information is hidden. So when you're talking about modeling in that way, you basically have to think about the construct that you have in Neo4j, the property graph, as being essentially, I have an assertion, actually two assertions, two triples. The first says Liz marriage one Richard. The second says marriage one is, references a marriage or references married. And, that property that you're talking about then is, you're replacing one assertion with two. So, if you do that, just about everything else, there's a couple of other minor edge cases, but just about everything else in Neo4j can be modeled in RDF. And that's really the key thing. Now, there's a concept that I mentioned earlier called reification. And reification basically is something where you say, I have a particular node that describes a relationship, and I can use that node as essentially a relationship between two things. And I can use that node to then act as a proxy for the kind of work that I'm doing, for the kind of statements that I'm making. That way, when I'm dealing with this, I can talk about, there are two marriages because each reifier is different from one to the next, even though the three properties that you have are basically the same. And that piece, that little reification piece, is then something that allows you to do the reification that makes working with property graphs more or less synonymous with working with knowledge graphs. But you have to understand that going in, or you have to basically say, okay, these two are not incompatible. It's that reification that has to be there. Otherwise, if you're going in, you can say, look, I want to think about this in a different way. I basically want to say, okay, I have a marriage, and a marriage has two participating people, and those, and I'll not get into variations on that, but and those two participating people, therefore, have an identifier that is unique, and it's that uniqueness that needs to be captured. So, when you're doing it, you can do these kind of isomorphisms. You can basically make these. You just have to understand that in RDF, you are always talking, you're generally wanting to talk about, this set of concepts are unique in and of themselves when I specify them, or I have, there's essentially one more piece of information that I need to be able to make them unique. So, I've seen reifiers basically discussed as maybe we need to be thinking about quads. Maybe we need to be, and quads are a little bit different than the way that we talk about graphs, but a graph can be thought of as being a kind of reification in its own right when you talk about named graphs.
And for you, where do vectors and vector databases fit into the architecture of using, for example, implementing RAG, or how have you used it in the past to help to drive truthfulness or accuracy in the system?
Okay. So the primary, well, there's several different things that you can do. One of the challenges, and this actually gets back to what I was talking about a little bit earlier,
Mhm.
about how you deal with clustering of information. That clustering of information is a consequence of it's the architecture for, or the
Mhm.
reason for having a vector database. So normally, when you talk about how are two concepts similar, what you're actually doing is saying, I have a definition, and that definition for this particular entity has a number of properties. And those properties are going to not just be values, but they're also going to be structures. How similar are these two structures? If I talk about a class, a class, now I'll kind of step back a little bit on this, but when we talk about a class can actually be thought of as a collection of things. And you don't actually have to specify how those things happen to be in that class. You only have to specify that they are. The specific metrics for being able to define how these things are in there, those are what schema is all about. Those are the things that say, I have a structure that effectively creates that. Now, the problem with the vector database is that structure gets squished and washed away. You don't, normally we're dealing with information that comes from, as Michael's pointing out, you're saying I have data that's been fragmented into 4K chunks, and each 4K chunk essentially has its own conceptual awareness or conceptual mapping into this information space. But realistically, it doesn't really tell you much about structure. So when you talk about graph systems dealing with vectors, what you're usually doing is saying, I have to have an encoding that will allow me to say not necessarily what's in there, but what is the best representation of this particular graph as a vector. And that particular representation can then be thought of as, there's a number of different ways. There for a simple graph, there's actually a graph to vec encoding. There's also a specific RDF to vec encoding, which is much more useful in my particular way of thinking. But again, I'm an RDF guy. And in both of those cases, what you're doing is saying, I have a mechanism for doing traversal from a given node to all of the nodes that are around it. And they may be directed, they may be undirected. The exact mechanism is pretty much depending upon what configuration you set up with. And that in turn allows me to create some kind of a vector encoding, what's called an embedded graph encoding, that allows me to then say these two things are roughly similar because their structures and their values are roughly similar. These are expensive computations to make in something like Sparkle, because you have to actually know the structure and know what you're dealing with to be able to do that, or you have to traverse it and then basically use something like a shackle to assign weights to different particular paths within that structure. But that's essentially how you take that information and you encode it so that it can be utilized by vectors. It's not that the information is being utilized, only that the direction, the vector,
The direction, yeah.
is basically there.
And this is an important point. We have a forum where we're going to have this panel discussion, including Kurt and Michael and Prasad. And so I want to pick this up in the forum as, a point of discussion, because there's different implementations and applications of vectors using graphs where it's not simply trying to facilitate organization of concepts, but actually help to enable RAG implementations, different types of architectures and data architectures to assist AI in truthfulness and accuracy and precision and all of those good things. So Kurt, thank you so much for joining and for this time to chat. I wish we had an hour more to discuss because I have so many more questions. But we have a little break before Marianne speaks with Scott. And we look forward to you joining us for the next session. Thank you.
I'm looking forward to it. Thank you very much
Yeah.
and appreciate the interview.